Hello, everyone. Good morning, good afternoon. Thank you all for joining today's webinar. We really appreciate the time you're taking to be here with us today. We have an exciting webinar and content ready and prepared to share with you. In this webinar brought by Vishay is accelerating power designs with advanced silicon carbide MOSFETs. And so we're going to have our presenter, Ardeshir Smiley, go through and explore how Vishay's silicon carbide MOSFET technology enables higher efficiency, improved power density, and faster switching performance across next-gen power systems from EV powertrains to AI data center infrastructure. As demand grows for more efficient, high-power electronic systems, SiC has become a critical enabler across automotive, industrial, and energy applications. So looking forward to having Ardeshir go through this content with us. Just a few housekeeping things here. The webinar will be a pre-recorded webinar. So I will switch over to that recorded webinar. And then we will be joined later by Ardeshir and the Vishay team to join us during a live Q&A. So while you're listening to the webinar, if you have any questions, please feel free to use the Q&A feature in the GoToWebinar panel, and we will make sure we get to those questions shortly after the content is presented. So I will then now switch over to the webinar and enjoy the content.
Good morning and good afternoon, depending on where you're joining from, and welcome to Accelerating Power Electronics Design with Advanced Silicon Carbide MOSFETs. My name is Ardeshir Smiley, and I lead technical marketing and product definition for automotive silicon and wide bandgap technologies at Vishay. In this webinar, we'll explore how Vishay's silicon carbide MOSFETs enable higher efficiency, greater power density, and faster switching from EV powertrains and power electronic subsystems to AI data center infrastructure. Let's start with an overview of the key power semiconductor switches and how they compare in peak power capability and switching frequency. Thyristors have long delivered a strong high current and high temperature performance, along with excellent peak power capability. However, they are limited by their lack of turn-off control and restricted flexibility in switching speed. Silicon IGBTs, up to now, have dominated industrial motor drives and AC-DC conversion, offering high voltage and current capability. But IGBTs suffer from high turn-off losses that limits efficiency in high power applications. For that, IGBTs typically operate below 50 kHz switching frequency. Superjunction MOSFETs, particularly those with fast body diodes, have significantly improved efficiency in modern power electronics designs. Their voltage capability remains limited to around 650 volt to 700 volt, which prevents their use case in many 800 volt high power application. While each of these aforementioned technologies brings distinct strength, they also have inherent limitations. Silicon carbide overcomes many of these constraints by delivering high voltage, and current capability, along with superior thermal performance, enabling greater efficiency and faster switching speeds. GaN, as a separate topic, excels in very fast switching for low to mid power applications. However, it does not yet match silicon carbide performance in high voltage and high temperature applications. At Vishay, with more than 100 silicon carbide patents worldwide, we focus on 3 technology pillars, providing solutions based on customer applications and requirements. Silicon carbide die in the form of known good die to meet the needs of module makers for a variety of power conversion applications is a core pillar of our technology. The second pillar, silicon carbide discrete devices for board level design flexibility with focus on transistor outline and top-cooled packages. And the third pillar, silicon carbide gel-filled and transfer molded power modules to deliver high power density with improved thermal efficiency. Let's look at the key applications driving the adoption and growth of silicon carbide in modern power electronics. Starting with residential and commercial energy storage, where advanced topologies such as T-type inverters, phase-shifted resonant converters, and dual active bridges are widely used to improve efficiency and power density. Moving to AI and high-performance computing data centers, where power demand continues to increase, with server racks now exceeding 150 kilowatts of power, these systems typically rely on architectures such as 3-phase VNO PFC combined with 1 or more isolated DC-DC stages to achieve higher efficiency. And finally, automotive high voltage power electronics, which helped establish the silicon carbide market through large scale adoption in EV traction inverters and onboard chargers. Here, a similar topology incorporates a PFC stage for single or 3-phase input, followed by 1 or 2-stage isolated DC-DC conversion. Across all these applications, silicon carbide MOSFETs, whether in discrete or module form, play a critical role in delivering higher power, higher efficiency, and improved system performance. At Vishay, we have made long-term investments in internal silicon carbide MOSFET and diode technology development. To accelerate innovation and time to market, we expanded our capabilities through the acquisition of Max Power Semiconductor, advancing our high-density planar platform, branded as MaxSiC2, with multiple products launched in 2025. MaxSiC2 is now in production with a focus on 750 volt, 1200 volt, and 1700 volt devices with capability of extending to higher breakdown voltages. Our next generation breakthrough technology, MaxSiC3, introduces a shielded dual trench structure designed to reduce a specific resistance and enable die size reduction, delivering a competitive improvement in both performance and cost. Across generations, our focus remains on reducing on-state resistance contributions from the channel, JFET, and drift regions to drive continuous efficiency gain. In addition, our MAX SiC2 planar devices offer a low temperature coefficient of RDS(on), extended UIS capability, improved short circuit withstand time, and enhanced switching performance. In real-world applications, MOSFETs rarely operate at 25 degrees C. Engineers focus on RDS(on) performance at elevated temperatures because that is where it truly impacts efficiency and reliability. One key technical differentiation of Vishay's planar silicon carbide MOSFETs is their low temperature coefficient of RDS(on). This means our devices maintain superior performance as temperature rises. This slide clearly illustrates this technical advantage. While our device with maximum RDS(on) of 56 milliohm ranks number 5 at 25 degrees C junction temperature, it climbs to number 3 and number 2 at 125 degrees C and 175 degrees C, respectively, outperforming many trench and planar competing solutions under real operating conditions. Another key differentiation of Vishay's planar silicon carbide MOSFETs is the robust short circuit withstand capability, which is essential for handling fault conditions in motor drive applications. For a 1200 volt 80 milliohm device with a small die size, we achieve an impressive 3 microsecond short circuit withstand time at 800 volt bus. This capability delivers multiple benefits, simplifies protection circuitry, extends the fault detection window, enables a smoother soft turn off for reliable system protection. This combination ensures greater safety and reliability in demanding real-world environments. In this slide, we go over benchmarking of our 750 volt 40 milliohm MAX SiC2 planar MOSFET in a TO247 4-lead package against 2 leading competitors. The red efficiency curve representing our competitor's latest generation planar device, and the light blue curve representing competitor's latest generation trench device. The evaluation was performed in a boost hard switching topology with 250 volts input and 400 volt output switching at 200 kilohertz. This is a worst case condition for body diode hard reverse recovery. Let's examine the efficiency comparison between our device shown in dark blue and a leading high volume planar silicon carbide device on the market shown in red. As illustrated, our device outperforms the competitor across the entire load range, from light to full load. Compared to the light blue curve, which is a trench device, our planar solution delivers comparable efficiency at full load. At lighter loads, the light blue curve shows a slight advantage due to lower dynamic losses inherent to trench technology. This strong performance from our MAX SiC2 planar platform is driven by key design optimizations. That includes enhanced cell density, optimized epi layers for lower RDS(on) at elevated temperature, and improved switching characteristics. Similarly, in a hard switching buck topology, stepping down from 400 volts to 200 volts at 200 kilohertz, we observe that Vishay's Max SiC2 planar MOSFET outperforms the latest generation competitor planar device across the full load spectrum. At full load, Vishay's planar silicon carbide performance is comparable to the latest generation competitor trench device. As a leading supplier of passive and semiconductor components, Vishay solutions can populate up to 80% of a typical power electronics board. As a result, we consistently take a system-level approach to validate and benchmark product performance against key competitors in the market. In this example, we developed a 3.6 kilowatt DC-DC reference design based on a resonant topology to a step-down voltage from 800 volts to 48 volts. In addition to our Max SiC2 planar 1200 volt 45 milliohm device in D² pack, this reference design incorporates a broad range of Vishay semiconductor and passive components, which includes a topside cooled 80 volt 1.2 milliohm MOSFET for improved thermal efficiency, shown on the left side of this slide, as well as DC-link film capacitors, shunt resistors, transformers, standard resistors, and power inductors. This slide presents the system-level efficiency of the 3.6 kilowatt DC-DC reference design utilizing our silicon carbide 1200 volt planar device alongside 80 volt silicon topside cooled MOSFET. As shown, the design achieves peak efficiency of approximately 96.5% for an 800 volt input to 48 volt output at full load condition. The power losses are dominated by transformer and power stages. We also characterize performance at 42 volts and 52 volts, with all configurations delivering above 95.5% efficiency at full load. Now we are moving into another method for device-level testing. One of the most common early tests that designers use to assess the switching performance of silicon carbide discrete or module products is double pulse test. In a standard double pulse test setup, two controlled gate pulses are applied to the device in a test circuit with an inductive load. The first pulse builds up current in the inductor, while the second pulse forces the MOSFET to turn on and off under realistic operating conditions. This test allows us to measure key parameters such as switching losses, voltage and current waveforms during hard switching transitions, and parasitic effects such as ringing and overshoot. In the following slides, we present double pulse test measurements comparing our silicon carbide MOSFETs with key planar and trench competitors using the same pulse conditions and external gate resistors. If we compare the turn-off behavior of two devices from high-volume planar silicon carbide MOSFET suppliers, we observed that Vishay's 1200-volt silicon carbide planar MOSFET exhibits lower voltage and current ringing during turn-off. This results in improved efficiency and is key factor for better EMI performance. We also observe the competing planar silicon carbide devices show a snappier body diode, leading to higher peak reverse recovery current during hard commutation. As a result, these devices exhibit higher turn-off losses compared to Vishay's planar silicon carbide MOSFET. Here is a quantitative comparison of turn-on and turn-off energy losses for each MOSFET. As shown, Vishay's 1200-volt planar silicon carbide MOSFET exhibits lower turn-off losses driven by reduced peak reverse recovery current and minimized ringing. In addition, during turn-on, our device also demonstrates lower switching energy compared to the two competing planar devices. Specifically in the same test conditions, the turn-on energy E-on for our device is just over 1,000 microjoules, compared to the approximately 1,085 and 1,100 microjoules for the competing devices. This is a key differentiation as switching losses play an important role in hard switching high power topologies. Many key devices in our silicon carbide Max SiC2 planar MOSFET portfolio are now released and available for evaluation and purchase. This includes widely used 1200-volt devices with RDS(on) values of 45, 63, 80, and 160 milliohm in TO247 4-lead, 3-lead, and DS square pack packages, as well as a 750-volt 40 milliohm device in TO247 4-lead package. We also plan to introduce in Q3 this year our first 1700-volt planar MOSFET with a maximum on-step resistance of 925 milliohm. In addition, in early 2026, we released our first Max SiC3 trench silicon carbide MOSFET, a 1200-volt 40 milliohm device in TO247 3-lead package. These product releases mark an important step in expanding our portfolio across voltage classes and technology generations. We also benchmarked our Max SiC3 trench silicon carbide device using the same double pulse test concept to evaluate turn-on and turn-off switching performance. In this comparison, our 1200-volt 40 milliohm trench device is evaluated against two competitors' 40 milliohm trench devices. And the results show that our device in dark blue achieves a lower peak reverse recovery current under the same test conditions. This is a critical advantage as many hard switching topologies involve body diode hard recovery, which can induce high reverse recovery currents and increase the risk of device failure. In this final slide, I'd like to highlight the next step in our product roadmap. As we have seen in low to medium voltage MOSFETs, there is a clear industry shift toward top-cooled packaging. And this trend is now extending to silicon carbide and other wide bandgap technologies. Here, we introduce our first top-cooled silicon carbide package, the PowerPack 1521LR. This package is footprint compatible with the JEDEC standard QD pack, enabling a straightforward adoption. By enabling direct heat transfer from the silicon carbide die to the heatsink, it significantly reduces thermal resistance along the cooling path and supports lower junction temperatures under high load conditions. As the industry continues to push for higher power density, thermal performance becomes increasingly critical. This enhanced package allows for higher current capability within the same footprint, directly contributing to increased power density. We plan to offer this package across 750 volt, 1200 volt, and 1700 volt product families, with initial samples targeted for availability in early Q4 2026. For more information, please visit our website to explore our currently released and available silicon carbide products. You can also contact our local sales team and distribution partners to learn more about our upcoming silicon carbide devices. With that, we'll open the floor for questions.
Thanks, Ardeshir. That was a really great content, and appreciate you putting all that hard work into this presentation. Want to now open it up for Q&A, but real quick before we jump into that, I just wanted to mention that there will be a survey at the end of the webinar. So please, if you have a chance, fill that out once we end the Q&A. That would be greatly appreciated. The webinar has been recorded. We'll send out a recording link as a follow-up to this webinar. But with that being said, I'm going to kick it over to Ardeshir, and we're going to get into the Q&A. So if you haven't posted any questions, please do so now, and we will get to those as much as we can within the time frame. All right. So we have quite a few questions that came in, Ardeshir. So let's go through one of the first ones here. So we have a question that is, what is the required turn-off voltage for Vishay silicon carbide MOSFETs?
So in terms of planar and trench devices that we have released, we don't mandatorily require a negative turn-off voltage. So if you look at our planar device section in the data sheet, we have a recommended gate source voltage, which that goes from -3 or -5 volts to 18 volts. But that is a recommendation, and the negative voltage for silicon carbide, in order to turn off and prevent false turn on, is all dependent on your application and your switching profile. So for planar device, we recommend negative voltage, whereas for trench device that is published on our website on the data sheet, we recommend VGS operating between 0 volt to 18 volt. But it all depends on your applications, depends on the transformer that you are utilizing, how leaky the transformer is, how fast you're transitioning in a hard switch topology based on your DIDT, DVDT. In some cases, the designer may need to also apply a negative voltage to trench device to ensure that it is fully turned off.
Great. Thank you for that. Moving on to the next one. Do you plan to continue offering planar SiC MOSFETs? And will there be additional 750 volt and 1700 volt devices in your portfolio?
Absolutely. So planar and trench structure each have their own distinct advantages. If you look at the planar structure, they offer higher UIS capability. As I stated during the presentation, they come with lower temperature coefficient of RDS(on), whereas trench device, it offers a lower figure of merit. And that is due to a smaller die size that can achieve a comparable RDS(on) to a larger planar die size. So our strategy is to continue and support planar and trench in parallel. And indeed, in the next few quarters, we will be releasing additional 750 volt, 1200 volt, and 1700 volt as part of our both planar and trench process technology.
Great, thank you. All right, the next one we have here, are there no Kelvin source packages for the Trench Max SiC3 family?
So the part that we have released with Trench 1200 volt 40 million, and that is published on our website. It's the first part we released in Q1 this year. That part doesn't come with Kelvin source. But any additional parts that we will be releasing to market, either transistor outline package or what I presented with the first top cooled silicon carbide package we are offering to market, they will all accommodate a Kelvin source connection. And this is critical because silicon carbide itself is a very fast device, and you require to have a Kelvin source connection to create a feedback to the gate driver, so that you can minimize any type of ringing across VGS or across the current and voltage waveforms.
Thank you. Another one we had for you. What is the key reason for Vishay's low reverse recovery current compared to others?
So it comes to the structure of the cell density that we have implemented, and if we compare to the planar structure, and if we compare to trench structure, it comes into the shielding. As I stated, it's a dual shielded trench structure. As compared to other competitors that you see in the market, they take either a gate trench approach or any other trench concept that they have been exploring and releasing to the market. So it comes with the device physics elements of our structure, which has to do with the shielding technique that we implement.
Okay, thank you. We have a couple more here for you, and then we can wrap up and send out the recording. So the next one I have for you is how do the gate resistance, how is it comparable for Vishay SiC MOSFET?
So that's a good question. So gate resistor, intrinsic gate resistance of the silicon carbide MOSFET is primarily influenced by die layout. And that includes a number of gate fingers that we implement on the die design. So if you go with larger die sizes, which translates to lower RDS(on), with the structure of the gate fingers, we achieve lower intrinsic gate resistance. And as we go with smaller die sizes or higher RDS(on), we achieve a higher gate resistance. So if you look at our planar devices that have been released to market and a datasheet available on the website, the 45 million 1200 volts, which is a larger die size, it comes with a gate resistance of 2 to 2.5 ohm. And as we go to 80 million or 160 million, that means it's a smaller die size because of the position of the gate finger and also the poly gate sheet resistance. It comes with a higher intrinsic gate resistance. So it's well related to the die geometry and the position of the gate fingers.
Great. Thank you. And then we'll do one more here, and then we'll wrap up. For Power Pack, the 15 by 21 LR top cooled package, you showed first samples in Q4 of 2026. What is the breakdown voltage and RDS on for that?
So as I stated, this is our first silicon carbide top cool package that we are introducing to the market. Some of the features is the low source inductance and lower RTH as compared to other top cool packages that are available in the market. And we intend to release 750 volts and 1200 volts with variety of RDS on targets and spec, and later extending to 1700 volts and higher voltages in the future. I would suggest if you have interest to learn about what RDS on spec we are releasing this year and also in Q1 2027, please reach out to Vishay Sales and FAE, and we can discuss the full roadmap related to silicon carbide devices that will be offered in this top cool package.
Okay, great. Well, Artie, thank you so much for not only putting this webinar together and going through the Q&A. This has all been really helpful and informational. I hope the attendees here have also found that as well. I think we could do maybe one last question, and then we'll wrap it up and get everyone on their way here. So we have one last question here for Artie there that just came in. Will you show some dummies of the top cooled package at the PCIM fair?
Certainly we can. We do also have some available samples in 1200 volt 40 million as engineering samples. But certainly, yes, we can discuss. If you stop by our booth at PCIM, we'll be showcasing our Power Pack 1521 LR top cool package.
Great. We'll be looking forward to that. So again, thank you everybody for your time today. We hope you found this helpful, and thank you to Artie and the team for pulling this together. Like I had mentioned, please take the survey at the end of the webinar here, and then we'll be in touch in the next couple of days with the follow-up with the link to the recording of this webinar. So please feel free to share that with any of your colleagues. And if you're interested in any of the content that Artie has gone through today, please reach out to us, and we'd be happy to connect with you and answer any and all questions you have. So thank you again, everyone, and have a great day.